Howdy, this is Mr. Potter. In our last video, we talked a lot about different types of sequences in series. We talked about arithmetic and geometric sequences in series. And today I want to take a little bit more exploration into this concept of what the geometric series actually means for us in our class. So you may recall from our last lecture that when we talk about a geometric series, we usually have some initial term and some ratio where each term in the sequence is basically the previous term times that common ratio. So I've got a plus ar plus ar squared plus ar cubed, and so forth. Now, my nth term of this sequence is going to be a times r to the n. But if I continue this infinitely, the formula that we had for the sum of an infinite geometric series was a over 1 minus r, and this was under the caveat that my r had to have a magnitude that was less than 1. What I want to do is I want to take this series and I want to manipulate it so that it looks something a lot more like what we would expect from algebra class. So what I'm going to do is I'm going to let a be equal to 1, and I'm going to let r be x. In other words, instead of dealing with a common ratio, I really want to deal with this as a variable that we'll be able to treat later on. And so this sequence becomes 1 plus x plus x squared plus x cubed, and so forth up through and past x to the n power. And this is going to be equal to my first term over 1 minus x. This is a rather interesting idea because it takes into account these polynomials that we've been dealing with since the very beginning of the class. They're relatively easy to deal with from a calculus standpoint. It's very easy to take the derivative or to take the antiderivative of a polynomial function. But dealing with rational functions tends to be a bit more problematic. And so what we're able to do here is we're able to do two things. One, we have this idea that I can replace a rational function with a polynomial function. But two is the idea that I have this notion of an infinite polynomial, a polynomial of arbitrary degree that basically increases to infinity the degree of this polynomial. So this is an interesting notion, and I want to kind of explore it a little bit. So I want to talk about it from the sense of substitution, because what I could do is I could replace x squared. And so the series would become 1 plus x squared plus x squared squared plus x squared cubed, and so forth. And my nth term would actually be x to the 2n power. And this would end up being 1 over 1 minus x squared. And so I can actually come up with different rational functions based on how I substitute for x. Now, the thing I do have to watch out for is I have to watch out for this notion of my x has to be bound between -1 and 1. And this concept here is actually called the interval of convergence. In other words, for x values that lies between -1 and 1, this summation will end up exactly being this rational function. And outside of this domain, it's not necessarily going to be. As a matter of fact, if I'm looking at this from if x equals 1, 1 minus 1 is 0. This, if I'm exploring as x approaches 1 from the left, this approaches negative infinity. This series here would be 1 plus 1 plus 1 plus 1, which also approaches a positive infinity as x gets closer to 1 from the left side. So I really don't understand the behavior at the endpoints of this interval of convergence, which is why I can't include the equality. And I don't know how the relationship is outside of this interval of convergence. And this is something we'll explore in later lessons. Now, for this series that I've just developed here, I've got this 1 over 1 minus x squared, so x squared must lie as the absolute value must be between 0 and 1. So x, again, must lie between -1 and 1. Now, the thing is, my interval of convergence is not always going to be between -1 and 1. I could do some transformations like we're familiar with from our algebra classes. So I could look at the series of 1 plus x minus 2 plus x minus 2 squared plus x minus 2 cubed. So my generic term would be x minus 2 to the n power. And if I continue this, I should have 1 over 1 minus my common ratio of x minus 2. But I can manipulate this algebraically by distributing the negative. So the x is still negative, but this 2 becomes positive, and this really becomes 1 3 minus x. So not only can I change this term in this geometric series function, but I can also change this constant. And this series is going to converge as long as x minus 2 has an absolute value that's less than 1. In other words, this value lies between negative 1 and 1. But if I solve this, I find out that x actually ends up being between 1 of 3. This is my interval of convergence for this function. So translating it to the left or to the right is going to translate that interval of convergence the same number of units to the left or to the right. Now, I certainly could take a look at it from another standpoint. I could take a look at it as 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed, and so forth. So this would be 1 minus x to the n power. That's my arbitrary sequence term. But if I continue, this is going to be 1 over 1 minus the expression 1 minus x. And when I distribute this negative, this actually ends up being 1 over x. So I've got this function that actually behaves just like my reciprocal function, as long as the absolute value of 1 minus x is less than 1. In other words, this is my interval of convergence by subtracting 1 from both sides and then multiplying through by negative 1. So this is my interval of convergence. And it's important to keep in mind this interval of convergence, because outside of this interval of convergence, even at the end points, this equality is not necessarily going to hold. At least it's not going to hold for a well-defined function. Clearly, there's an issue when x equals 0 for this function and for this function. But I could also do something a little bit more complex. I could take a look at 6 plus 3x plus 3 halves x squared plus 3/4 x cubed, and so forth. So my terms are actually 6 times x over 2 to the nth power. And looking at this from a geometric series, my first term was 6, and my common ratio was 1/2 x. But if I was to try and simplify this would actually be 6 over 2 halves minus x over 2, which really ends up being 12 2 minus x. So I can actually reach all three parts of this fraction using an appropriate a and r. So I can take a look at these manipulations, and also because x over 2 is my ratio, my interval of convergence actually does something a little bit interesting, because x over 2 must lie between -1 and 1. My interval of convergence actually ends up being from -2 to 2. So the thing is, I can set this up in such a way that my interval of convergence is a little arbitrary. So I actually have a lot of control with this geometric series, and I have a lot of ways to manipulate it so that it looks like what I want as a rational function algebraically. And one of the kudos about this is the fact that if I wanted to figure out what 1 over x is for some particular value, all I needed to do is substitute enough terms of this polynomial, and I can get whatever degree of accuracy I want. That's really one of the powerful ways that this is used, and we'll talk about that later on in another video. Of course, this is, a calculus class, so I should be able to manipulate things from a calculus standpoint. So let's take a look at if I had 1 plus x plus x squared plus x cubed plus so forth. Now I know that this is 1 over 1 minus x, but one of the things that we've talked about here is that if I take the derivative of one side, that should be equal to the derivative on the other side. So in other words, that means that 0 plus 1 plus 2x plus 3x squared plus so forth, and now my individual term would really be nx to the n minus 1, just like the power rule states, would have to be the derivative of this expression. Now keep in mind what I'm really taking the derivative of is 1 minus x to the -1 power. So the chain rule would say this is -1 times 1 minus x to the -2 power times the derivative of what's inside my parentheses. So this really ends up being 1 over x minus 1 squared. And so through this calculus, I can actually change the degree of this term here. So I can actually do quite a bit of manipulation. But what's really interesting is when I try and go the other way. In other words, if 1 plus x squared plus x cubed is really equal to 1 over 1 minus x. What happens if I try and find the antiderivative of this? And so what I find out is taking the antiderivative on this side, I get x plus x squared over 2 plus x cubed over 3 plus, and of course my generic term would be x to the n plus 1 over n plus 1. But what happens is when I'm taking the antiderivative here, I'm going to have to let u be 1 minus x. Du would be negative 1 dx, which I don't have. So this becomes the integral of 1 over u times negative 1 du, which is really the negative natural log of u. And so this brings up something that's really interesting. The idea that I could take some polynomial, and this polynomial, as n goes to infinity, not only is it equal to a rational function, but could be equal to some completely different transcendental function. This is calculus after all, so if we're going to use calculus, let's use it to our advantage. I know that if I was to find the integral of 1 over x, I know that that is natural log of x. So if I could get my 1 over 1 minus some variable expression to be equal to 1 over x, then I'd have something that would actually give me the natural log function without all of this other information that we have here. So I'm going to need a x to become positive, which means inside this parentheses it really needs to be negative. And I'm going to get rid of adding a 1, so I'm going to need to make sure I subtract a 1. Now we've seen this term here in a previous example, so let's go ahead and explore this. So if I'm going to integrate, I'm looking at 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed plus and so forth. And these terms are really 1 minus x to the n. Then this should be equal to 1 over x. And if I'm able to find some way to integrate this, then I should end up with the natural log of x. Over here, though, I need to make sure that I'm integrating all of these terms, so I really want to let u be 1 minus x, so du is negative 1 dx. And none of these terms are negative. So I need to compensate for that. So dx would really be negative 1 du. And so integrating this is going to give me, this really becomes the integral of 1 plus u plus u squared plus u cubed, and so forth. But with a negative sign in front, so this really becomes u negative minus u squared over 2 minus u cubed over 3 minus u to the 4th over 4, and so forth. And it ends up being a negative u to the n plus 1 over n plus 1. But this is really negative 1 minus x minus 1 minus x squared over 2 plus 1 minus x cubed over 3 plus 1 minus x to the 4th over 4, and so forth, being negative terms as well. But this will be equal to the natural log of x. And so just by simply algebraically manipulating my a term and my r term for my geometric series, I actually have an infinite polynomial for natural log of x. In other words, if I wanted to know what the natural log of say 0.5 is, then all I need to do is substitute 0.5 into this sequence. So this really should be equal to negative 0.5 minus 0.5 squared over 2 minus 0.5 cubed over 3 minus so forth. And I should be able to go as many terms as I want to get whatever degree of accuracy I want. But that's not the only place that this is useful. I know from calculus that the integral of 1 over 1 plus x squared dx is tan inverse of x. So if I can find some way to manipulate my series so it looks like this, I should have some really interesting results. So what I'm looking for is I want 1 over 1 minus r to be equal to 1 over 1 plus x squared. And so my r really ends up being negative x squared. And so I'm looking at a series that goes like 1 minus x squared plus x to the 4th minus x to the 6th, and so forth, where it's really negative x squared to the n, which you'll often see written as negative 1 to the n x to the 2n. And this will equal 1 over 1 plus x squared. Integrating this dx gives me tan inverse. Integrating this with respect to x gives me x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus x to the ninth over 9 minus and so forth. Now if this is tan inverse of x, then I should be able to get a real good approximation of what pi is, because I know that the tan inverse of 1 is pi over 4. But according to this formula, this is really equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus so forth. And so this brings up a result that Gauss actually worked on as an approximation of trying to find a value of pi. And this is a series that actually will give me pi to whatever accuracy I want. Notice that I'm able to get pi, which is a geometric value, from something that's just polynomial. Granted, it's an infinite polynomial, but it's an interesting result. Now, one of the issues we have is this question of well, wait a minute. Wasn't our interval of convergence between -1 and 1? So how can x equals 1 work? And that's something we'll have to talk about in a later video. So this is Mr. Potter. Thank you for watching. Have a great day.